Hello everyone, this is Dr. Lennon, and we're going to continue today with exponential functions. So today we'll kind of try and look at them from a functional perspective, but maybe review a few things at first. So last time we saw an exponential function had the form well, it had one of two forms. So either you had standard form, which looked something like f of t equals a times b to the t, or we had the continuous form, which looked like f of t equals a times e to the kt power. So those are the two forms using function notation. So one of the first things we did that, again, is on the homework is identifying the exponential function that passes through 2 points. So let's go ahead and do 2 of those examples. So we'll kind of look at a case maybe we didn't look at last time that actually makes things a bit easier. So find the exponential function that passes through the pair of points, or the given pair of points. So the first one is a little bit different from last time. So the points are going to be 0, 8, and so this is kind of, I've made it so it works out nicely, but this has got a lot of decimal points. So 0.013824. So the interesting thing to note here is this is your y-intercept. So when you look at your exponential form f of t equals a times b to the t power, one thing that we know is 0, a is the y-intercept. Just to note that if you plug in 0, it's pretty apparent because you get a times b to the 0 power, which is just equal to a. So that is the reason why that 0, a is the y-intercept. So in this example, we actually can jump straight to the fact that we know our function has to look like f of t equals 8 times b to the t power. So we're not going to have to take ratios this time using these examples. So that's all we have to do is plug in that second point. So we're going to plug in 3 for t and this 0.013824 for f of t. So we get 0.013824 equals 8 times b to the third power. And then to solve this, we're going to divide by 8, and then we're going to have to take the third root. So this comes out to 0.01728, and again, that's equal to b to the third power. Again, b's, so here we can either take the cube root or raise both sides to the 1/3 power. Usually I like to use the exponent because not every calculator has a cube root button. So if you do b to the third to the 1/3 power, we end up with b on the right-hand side, and on the left-hand side, we just end up with 0.12. So that tells us that our exponential function here is just f of t equals 8 times 0.12 to the t power. So I would say when one of those 2 points is the y-intercept, it saves you a little bit of time, so you don't have to spend quite so much time taking ratios and solving for both things. So it's a little bit shorter. Again, you could still use the other method we went over last time. So let's go ahead and review another type of the question that we looked at last time, where we're looking at the exponential function that passes through 2 points, but one of those points is not the y-intercept. So this time we're looking for the exponential function that passes through 5, 15, and also the point 7, 18.15. So what we want to do is plug both of them into the exponential equation. So plug both into f of t equals ab to the t. So again, the first coordinate is your t value and the second coordinate is your y value. So again, remember I like to plug in the one with a larger t coordinate first. That way when you subtract them, you have a positive exponent. So 18.15 is equal to ab to the 7th power, and 15 equals ab to the 5th. So we can take ratios to put them together to create a equation that only has a single variable. So again, we are making fractions, so 18.15 divided by 15 equals ab to the 7th over ab to the 5th. So if you plug that into your calculator, you get 1.21 equals b squared. So b is going to be the square root of 1.21. Again, typically this equation would have two solutions, but because we require for exponential functions b to always be positive, we can just consider the positive square root. So 1.1 is the value of b. So in this case, once we solve for b, we're not done. A is not given to us immediately, so we need to look at the form of our equation, which is f of t equals a times 1.1 to the t power, and then we can plug in either of the 2 points. So I'm going to plug in 5, 15. So 15 replaces f of t, and 5 replaces t. So let's go ahead and write that. So let's see, so what do we have to do now? We have to divide by that value, so we're dividing on both sides by 1.1 to the 5th power. Again, you need to be a little bit careful with parentheses when you put this into your calculator, but if you do it properly, you should end up with, if we round to 2 decimal places, 9.31 is approximately the value for a. So our exponential function looks like f of t equals 9.31 times 1.1 to the t power. So that is the equation. Okay, so we looked at a few compound interest formulas and things like that last time, but what I want to do today is look at these from the functional perspective. So let's go ahead. On the homework, I have a couple examples where you have to write a table of values and graphs. So let's do that with the two most basic exponential growth and decay functions. So example, so let's make a table of values. And sketch a graph. Of each function. So for a, we have f of t equals, let's say, 2 to the t power. So our table of values, we'll have our input values t, and our output values, we'll just call them y rather than f of t. But basically, we have your input-output coordinates. So I'm just going to choose -3, -2, -1, 0, 1, 2, and 3. So you want to plug each of those into the exponent. So you have 2 to the -3rd, 2 to the -2nd, 2 to the -1st, 2 to the 0, 2 to the 1st, 2 squared, and 2 to the 3rd. So you can simplify each of these. This comes out to 1/8, 1/4, 1/2, 1, 2, 4, and 8. So each of these is a set of coordinates that we can go ahead and graph. So let's see, we need our input values to go up to at least 3 to the right and -3 to the left. And the output values are all positive, and they go up to 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So the first coordinate is -3, 1/8, so that's somewhere down here, some point there, and then -2, 1/4, -1.5, 0, 1, 1, 2, 2, 4, and 3, 8. So we see our exponential function is passing through all of these dots. So it's this curve that does that. And again, sometimes it's a little bit tricky to draw these by hand, but you're just getting an idea of the curve. So this is f of t equals 2 to the t. All right, so that is, again, an example of exponential growth. Remember, it's exponential growth when, okay, so there's kind of two cases, either when b is greater than 1, or we can have it when r is greater than 0. So remember the relationship between r, which is the percent change, and b, which is the exponential rate, is b is equal to 1 plus r. So in this example, since b is equal to 2, that means r has to be equal to 1. So when you have a function that's doubling the output each time, that means that the output is increasing by 100% each time step. So b, let's look at an exponential decay. Let's look at one that's just kind of analogous. Let's look at, let's say g of t equals 1/2 raised to the t power. So again, we want to just first make a table of values, and I'll use the same input values. And actually this one, if you look at the table, you're going to have very similar output values, except they're going to appear in the reverse order. So we're going to go from -3 up to 3, and we're going to increment our input values by 1. So again, this will be 1/2 to the -3rd, 1/2 to the -2nd, 1/2 to the -1st, 1/2 to the 0, 1/2 to the first power, 1/2 squared, and 1/2 to the third power. And this comes out to +8, +4, +2, 1, 1/2 or 0.5, 1/4 or 0.25, and 1/8. So what happens now when we look at the graph of this exponential function? Basically, it's going to have the same shape, but it's going to be reflected about the y-axis. So we can graph all those same points. So at -3 this time, we're now at +8 as our output value. -2, we are at 4. -1, we're at 2. 0, we have a y value of 1. Then we go to 1/2, 1/4, and 1/8. So our exponential function is the one that passes through these points. And this is our exponential function in this case. So this is exponential decay. Which means the function is decreasing over time. So this happens when b is between 0 and 1. So 0 is less than b is less than 1. Or if we look at the percent change, this happens when r is less than 0. So those are two examples of how to create a table of values and graph. We can also do this quickly by looking at, say, Desmos, the graphing utility, and just plotting these values here: y equals 2 to the t, or y equals 1/2 to the t. Oops. And we see both of those graphs that we draw. So we notice that they're just actually mirror images about the y-axis. And you can click on either one of these icons to make one or the other disappear. Okay, so those are the two graphs. So let's talk about the domain of these functions. It's pretty straightforward. So we can talk about graphical properties. So graphical properties. Which we care about for all of the classes of functions we study. So one, what is the domain? The domain, so let's say graphical properties, we'll say given a general exponential function, f of t equals ab to the t. We're just considering it in standard form. So given a function that looks like that, the domain is all real numbers, which in interval notation we can write from negative infinity up to infinity. Basically, if you look at either graph to the left and to the right, the graph appears everywhere. So it has all real values. When we look at the range and we look at, so those are all the possible y values, notice, so if you look at the domain, it's going everywhere to the left and to the right. But when you look at the range, you're asking yourselves how far down and how far up does the graph appear? Well, the exponential quantity is always going to have a positive output value. So our range is in fact just the positive real values. So this is going to be 0 to infinity. And one of the reasons is if b is greater than 0, which we require, well actually in general we say a and b are both greater than 0 for an exponential function. So if a and b are greater than 0, then the output quantity, a times b to the t, is greater than 0 for every t value. So for all possible inputs, we're always going to have a positive output. So that's why the range is all positive values. So then 3, there's kind of two parts. A, if b is greater than 1, that's exponential growth, that means our function has to be increasing. Then f is increasing on its entire domain. And we saw the second case, exponential decay, occurred when b was between 0 and 1. So if b is between 0 and 1, then f is decreasing. On its domain. And maybe the last thing we can talk about is f of t will have a horizontal asymptote y equals 0, which is just the x-axis, and a, that's going to be to the left in the case that b is greater than 1, so that's exponential growth. It has the asymptote to the left if b is greater than 1, and part b to the right if we are experiencing exponential decay. So that occurs when the base is between 0 and 1. So those are pretty much the main graphical properties that we have with regards to exponential functions. We can also talk about translations, which maybe we should make a mention of. In general, this happens with functions. Let's say translation properties. So let's make two constants. Let's say suppose h and k are positive constants. Then we can kind of write down four graphical properties. We can subdivide them into two parts, so we can talk about horizontal translations. So what are the two horizontal translations? So one, if we look at f of t equals ab to the t minus h in the exponent. So this is a translation of y equals ab to the t, right h units. If instead in the exponent, we did a plus h rather than a minus h. So f of t equals ab to the t plus h. What happens now is instead of going to the right, it goes left. So this is a translation of y equals ab to the t left h units. And basically what you can see is it's going to adjust where the y-intercept happens. The reason it goes right h units is if you plug h in for t, h minus h will be 0 in the exponent. So the y-intercept is going to be occurring at h rather than at 0 now. And if the typical y-intercept of a, rather than occurring at 0 in case 2, it's going to occur at negative h, because negative h plus h will be 0 in the exponent. The vertical translations are a bit more intuitive. So what you're doing is you're just adding k to the exponential quantity. So vertical translations are affecting the y value. So vertical translations, again, we can write down two cases. So we have f of t equals ab to the t plus k. What this is this is a translation of y equals ab to the t up k units. And if instead you change it to subtraction, so 2, if we look at f of t equals ab to the t minus k, this is a translation of y equals ab to the t down k units. So maybe we might think of an example. So we'll just graph this on the computer, but here's something you might want to think about. Pause the video before I go ahead and show the graphs. Is let's just take one of the let's consider the graphs we've already drawn, 2 to the t and 1/2 to the t. So let's say graph each function using translations. So let's say part A, we have f of t equals 2 to the t plus 3. Let's say b g of t equals, let's say 1/2 to the t power, and then after the fact we'll subtract 7. And then C, let's look at maybe h of t. Let's combine, let's do two translations all at once. Let's say 2 to the t minus 1 plus 3. So basically what we can see, so pause your video, think about what's going on here, what translations are taking place to the two graphs we drew. So basically A and C are going to be translations previously of this graph A, 2 to the t, and part B is going to be a translation of this graph 1/2 to the t that we did in part B in the previous example. So what do you think the translations are going to be? Well, this should take, this one right here, A, this should take 2 to the t left 3 units. 1/2 to the t should take 1/2 to the t minus 7 should take 1/2 to the t down 7 units. And the last one should have two things going on. It should take 2 to the t right 1 unit and up 3 units. So let's go ahead and see if our predictions prove to be true. Let me go ahead and, that 7 looks a little funny in this example, so let me rewrite that. So let's go ahead and do that. And let's go back to Desmos and see if our intuition was correct. So let's look at the first one. So we want to look at 2 to the t and do 2 to the t plus 3. So let's go ahead and make this graph blank. Let's go up into the exponent. So this is our graph 2 to the t plus 3. We said that should move everything left 3 units. So let's put a plus 3 up there and see what happens. Oh, it wasn't in the exponent, so I need to make sure that I'm in the exponents. So maybe I need to include parentheses. So 2 to the t plus 3, and as you can see, it moved everybody to the left 3 units. So maybe to make that more clear, we can add another function below. We can look at y equals 2 to the t. And you see, basically, it took the same exact picture and just moved everybody left 3. So the y-intercept that's at 0, 1 is now at -3, 1. Okay, so the second graph, we had y equals 1/2 to the t, and we did 1/2 to the t minus 7. So let's go ahead and look at this graph again. And we said the -7 should translate it down 7 units. So we have y equals 1/2 to the t, and then -7. So we get this graph down here. So look, everybody went down 7. It might be a little more clear if you zoom out. And we can see basically the y-axis, or the y-intercept on the y-axis at 0, 1 should move down to 0, -6, which it did. So this is a translation down 7 units. Okay, and then our very last one, we were again translating 2 to the t. So we were performing 2 transformations. So we were doing t minus 1 plus 3. So it should be going right 1. So t minus 1, and then up, I need a parentheses in the exponent. Apologies. So t minus 1, and then plus 3. So we saw that it did 2 things. If you look at this point, it should move right 1. So this value right here is 0, 1. Right 1 would be here, and then up 3 would be up 1, 2, 3. We see it falls exactly where we expect. Again, kind of, it's got a hair trigger here, so it's kind of difficult to put it on exactly the point, but we see that that's exactly how it was translated. So those are transformations of exponential functions. So sometimes you can look at a graph and recognize it as a transformation, and that'll allow you to recognize, say, like the domain and the range. So well, let's state that specifically. So maybe if we look at part C, so we can kind of do a part 2 example. So example, let's say identify the domain and range of our third example there, h of t equals 2 raised to the t minus 1 plus 3. So what happened? Well, let's go back and look at that graph. That's an easy way to figure it out. So if we delete this graph, we see that we're getting an asymptote now at y equals 3. It still goes everywhere to the left and to the right, so transforming it is not affecting the domain, it's only affecting the range. So the range is when we talk about the lowest y value up to the biggest y value. So it gets very near the lowest y value of -3, but never quite gets there and goes all the way up to infinity. So basically our domain is from -infinity to +infinity because the graph appears everywhere to the left and everywhere to the right. It continues ad infinitum in both directions, but when we look at up and down, it kind of stops when you get to y equals -3. So we can identify that pretty quickly from looking at the graph, which is a consequence of understanding the translation. So the domain here remains the same, all real numbers or -infinity up to infinity, and the range now starts at 3. It doesn't include 3, it just gets very near 3 and goes all the way up to +infinity. So that would be the domain and range, and that's very easy to think about once you understand the transformations. So anyway, I hope this helps. Again, have a look at the homework and let me know if you have any questions. So try and stay healthy, and I will talk to you soon. This is Dr. Lennon signing off.